So what you needed to do, you need to calculate the efficiency. Yes. सर NPTEL वाली वो भी हैं. Okay, so guys, did you calculate the efficiency and the output? So this happened to my camera. Whenever I try to apply software, there is a let's see effect. Okay, so I think okay, let's say. So guys, did you calculate the efficiency? Was it like the data is given? You just need to put the values in that. So let's say if you have something. So before going to that question, let me introduce you to this course. So basically, we were thinking of different solar thermal systems, and in the last class we had a good introduction about what are the different solar systems and how there are heat losses, like from a box type flat panel collector. Then you have to calculate the side loss coefficient, bottom loss coefficient, and top loss coefficient. So similarly, on these grounds, we'll be now studying further, and we'll go into much higher type of like complex type of thermal systems that are based on solars. So yeah. Okay, so I think you guys know what it took that numerical. So maybe it's not that hard. That's why I gave you guys, because I want you guys to be familiar with the systems. So until and unless you are familiar with the systems, you won't be able to uh, judge how this system works, how the efficiency are calculated, what are the different outputs, and what are the different inputs to their system. That is why it's very much important then to look into these systems, into the way in which we study the different efficiencies output of a normal systems. Okay, so before going that, let me start. I think uh, um, yeah. Okay, so yeah, my screen is presentable. Okay, so welcome you guys to the live session of this NPTEL course, that is Sustainable Power Generation System. This is live session 2 being conducted on 6th of August 2024. This course is being taught by Professor Pankaj Kalita, is Associate Professor at IIT Guwahati. I am Rohit, I am a pure scholar. This is my profile, so I won't go into detail because I have discussed it in the last class. Teaching methodology will remain same. Every Tuesday we will meet at 7 to 9 p.m. Then we will discuss the different topics, and then we'll go to the quiz questions. So these questions are from previous run of this course. Still, I will push you guys to ask more questions about the different concepts, different questions that can be uh, that are not understood during the course. And I will suggest you guys to please go through the lectures, video lectures, and I also track different discussion forum at regular intervals. So there were no question, only one question was there regarding this. The video was not playing or something, someone had posted. So if you have any question, you can also use the discussion forum. Okay, so let's start from this power generation cycle for liquid flat plate collector. So you guys must know that what consists of a flat plate collector. So flat plate collectors are essentially this type of devices. They are box type of structures which are glazing. Glazing means glass. and generally there are two blades. Okay, and then there is absorber surface. Their pipes are there, or if air is to be heated, then no one need to have pipes. Okay, they are liquid flat plate collectors. So whatever wavelength enters here, shorter wavelengths, they get converted to long wavelength because of this glass and get trapped inside, and the heat is transferred to the fluid or the material which is flowing through this. So this is actually a flat plate collector and basically used in providing water in houses. Like one of the example is evacuated tube collectors are very much famous for providing water to the uh, surface, or whatever the solar collector which you see in houses are basically liquid flat plate collectors for solar water generation, hot water generation. And there is a tank, so this is what is installed in your house. Okay, there are no booster meters. Okay, so now we want to use these to produce electricity, but to produce electricity you need to transfer that energy from whatever energy you have collected solar energy in the fluid, then it has to be transferred to some other fluid that will run through the turbine. So this is basically a ORC, organic Rankine cycle. Okay, so where the steam or the hot water, uh, basically because of the heat trapped from the sun to this storage tank in hot water, it gets transferred to refrigerants. Generally refrigerants are used R11, R113 or 114, and these refrigerants then flow through turbine, and then after turbine these are condensed, so turbine produces some energy. Okay, and then at 35 degrees Celsius, it is pumped back to the system. So this is how a low temperature power generation cycle using liquid flat plate collector use. So collector efficiency is 25%, this one. Okay, temperature difference in ORC, RC efficiency is 7 to 8%. Okay, ORC is organic Rankine cycle. Okay, and overall efficiency is basically you multiply all these values, so it comes out to 2%. So low temperature power generation cycle using liquid flat plate collectors are actually very much less efficient, so that's why they are not much used. Only it can be used in small scale power generation systems, because at 2% efficiency you are not bothered about the efficiency, you are just bothered about whatever power you can take out for running some small systems or something. Okay, so this is like a conceptual thing, but it can be implemented. Okay, then there is solar chimney power plant. So solar chimney power plant, the this is what the question I have given. So whatever happens, there is a big this disc type of surface made of glazing, okay, on the ground, and there is chimney, and there is this flow of air from all the sides. Okay, so when sunlight heats this, the air is heated and a convection current is formed. Okay, so this convection current flows upwards through the chimney, and it then makes these this what you say, you can say it turbine or wind turbine type of thing, or rotor to rotate. Okay, the fan to rotate, and because of it, it produces electricity. So yeah, this was basically suggested in 1970s, and basically it produced so this is not a conceptual thing, it has already been implemented somewhere. I think in Spain they have implemented it. So sunlight passing through the transparent cover causes air to trap in the greenhouse to heat up to 10 to 20 degrees Celsius. The energy conversion efficiency of solar chimney is low. So by low you means very low. Okay, so it is around 1 or 2%, or maybe even lower than that. But if you want to actually basically calculate the conversion efficiency, G into H by Cp into Ta is actually the formula for calculating the conversion efficiency. Now this was the question which I had given you guys for calculation. So basically it says a maximum possible conversion efficiency obtainable with solar and also estimate the efficiency of plant as a whole and daily output in typical summer months using the following. So turbine generator converts only 50% of the maximum available energy into electrical energy. Okay, collection efficiency of greenhouse is 25%, and for the summer months the radiation received is 6.5 kilowatt hour per meter square. So area is given, so whatever input you need to calculate. Okay, input is basically 6.5 into 50,000. So this is what is the input to this system. Okay, 6.5 into 50,000. So this comes out to be 3.325 megawatt hour. Okay, now this is the input energy. Now it says that 25% of efficiency will only be collected by this collector efficiency. So multiply it with input with 25%, that is conversion efficiency or collection efficiency. Sorry, not conversion efficiency, collection efficiency. Like 100 joules of energy is in the sunlight, but only 25% is what sunlight transfers to the gas or something. So this comes out to be, you multiply it with 0.25, 81.25. Okay, megawatt hour units you can write. Okay, now 81.25 is actually the energy available with the this greenhouse gas which traps the solar radiation. Now it will move towards this, and this rotor turbine generator converts only 50% of the maximum available energy. So maximum available energy is this for conversion, and it converts only 50%. So again you multiply it with 50%. Okay, so it comes out to be 0.5, 40.625. This is the output. Okay, 63, let's say, megawatt hour. Now the solar energy had 325 megawatt hour of energy stored with it, or contained in it, and but only if we could because of our system efficiency we could only get 40.63 megawatt of hour of energy or electricity in terms you can say. And because of that we if you think of these systems like in terms of E in by E out, you can say 40 upon 325. You can see the actual first. Okay, first law efficiency you can calculate. Okay, but we are more interested in conversion efficiency. What is the maximum conversion efficiency? So you can just use this formula. G is 9.81. Okay, H is the height of the chimney. So you can see the height. Normal floor of a house is 3 meter, and you have to build a chimney of 300 meters. So you can imagine you have to build 100 floor height this chimney to work. An area of 50,000 meters square is quite a big area. So and it will only produce 40.63 megawatt hour. Okay. So this is why these type of systems are actually less efficient and not looked into because of the perspective of maintenance, building, and the kind of comparison with other systems. So whatever system will be implemented on the, so one thing I want to make you clear here, because whatever system, there are many advanced system at various like various stages of research, and lots of work are going on to make this system efficient. But what segregates them and what doesn't make them implementable is the techno-economic analysis. Like feasibility of this system, economic feasibility. So if somebody is putting money into it, so the money has to come back. Okay, so if coal plants are more feasible than solar power plants, then probably all the investment will be in coal power plants. Okay, whatever uh, whatever things it takes, even if it's polluting or even if it's something which has done a lot of harm to the environment, but still a lot of things in the system is governed by this economic feasibility. But one thing people don't understand here, mark my words, one thing people don't understand here, that when you take a life cycle perspective of this, like when you take a life cycle cost, like coal power plants are cheaper to build, but the emission coming out of coal power plants, you need to clean that emission, air pollution control devices that are costly. Second thing is that when these emissions go outside, then it affects a large number of people, and people like cities in Delhi are smoke and all this, then you have to control that smoke also. So lot of money has to go on that also, so that is not accountable and not related to this cost of planet. So this is why life cycle cost analysis is also important and puts a perspective to what a proper fair comparison of these two types of system. So that's why I always say economic feasibility may be important for the businesses, but if government or any policy decision has to made, because government has to look for a broader perspective, broader view. So if any policy decision has to be made, then it has to be made on the life cycle perspective of this. Okay, so I was where we you just 300, and then CP of air is something, CP is 1.07 or something. So 1.07 was 0.717. Please check it. And then what is CP and TA, temperature of ambient air. So it's given 305. Okay, so you can calculate the maximum efficiency. 10 to 300 by 1.07 by 305. Okay, so you can calculate this maximum efficiency using this formula, and please calculate these type of question, because until unless you understand what these question are asking, you won't be able to actually solve the questions of the assignments, or maybe it will be very difficult for you guys to solve the question in the final exam also, because these questions are actually make a foundation of your knowledge. So whenever you try to learn some theoretical concepts, please go deep and solve the numericals also. So the numericals are actually kind of real world situation which you can solve it through and gain an understanding of. Okay, so let me see if any of you have any questions regarding this. Discard. Uh, okay, so no questions from you guys. No problem. Okay, so what if there is anything which you want to ask, please feel free to ask uh, anything, any questions regarding whatever we discussed, or something which you want to know, anything. It doesn't mean that you have to ask only numerical questions or something. You can ask anything. Okay. See, if anyone is very shy in speaking, so he can also write your questions here so that we can discuss on it. Okay, we want to take a look. Take a look also. Okay, so is there any questions? Surprisingly, no questions are asked by you guys, but I will suggest that you guys please ask some questions so that we can have a great discussion to the topic. Okay, so there was no problem. We can move ahead with the different things in the lecture slides. Okay, so I just had this blank slide. Okay, now another thing is that key you need to know the concentrated solar technology for power generation. So concentrated solar technologies are different. Photovoltaic generation are different. So in the next week you guys will understand the photovoltaic power generation. Photovoltaic power generation things mainly focus on generating electricity directly from the sun. Okay, solar energy, not sun, solar energy. So yeah, I should write it down here. PV, solar to, and this is direct conversion, guys. Then we have CST, that is concentrated solar technologies. These convert solar directly to, what do you say, heat. Okay, so in PV systems the main focus is electricity generation. In CST systems the main focus is heat. So if I compare these two systems, so these two are actually different systems, but PV is actually like, if I talk about average efficiency, so 22%, 18 to 22% efficient. Okay, and these are much more efficient, 40 to 48% you can say, 44% you can take an average. Okay, efficient. Okay, these are like this much efficient, but one thing is a catch here. PV produces electricity, so electricity is a very high grade of energy, and CST produces heat maybe at higher uh, efficiency. But the problem is that in the heat which CST produces is not a high grade of energy, it's a low grade of energy. So to convert it, or maybe the quality of energy which we get from CST matters a lot. So in energy we are more focused on the quality of energy rather than the quantity of energy. So okay, so I will give you an example here, that let's say we have uh, a heat source available at 50 degrees Celsius and another heat source available at 500 degrees Celsius. Both contain same quantity of heat. Let's assume that they contain 100 megajoule of heat, but this is 50 degrees Celsius, this is 500 degrees Celsius. So yeah, this will be much useful because the quality of energy is higher. This is not. Okay, because with 500 degrees Celsius you can easily convert it to electricity, generate electricity from that, but for 50 degrees Celsius you won't be able to convert it directly to electricity in steam power plant or something. So this is how the quality of energy uh, takes place. The role of quality of energy takes place. Okay. Now, now we have in concentrated solar technology, we have concentrated solar thermal, and we have concentrated solar PV. So we will not be dealing with concentrated solar PV in this lecture or this thing. So there are two types. One is medium and another one is high temperature. So medium temperature is parabolic trough and then Fresnel corrector. So there is low temperature also application also. but those are not concentrated. Those are like flat plate collectors, and the solar chimney is one of the low temperature. Solar pond is also kind of low temperature. And what is this parabolic trough collector? So there is a half semicircle cylindrical disk is there which focuses on a point, and this is not a point, this is called line focusing. Okay, it is a pipe on which it focuses. This parabolic trough, similar like Fresnel collectors, these are not kind of curvature disk, these are kind of mirrors which focuses sunlight to this. Okay, a central tower, there is a central tower. So there are pictures in the lecture slides, you can go and see. And there are heliostats, okay, surrounding this. These heliostats focus the sunlight to central tower, and then the fluid is passed through it, cold fluid, and then it converts to steam, and then uh, uh, electricity generated. Parabolic dish is basically dish which focuses on a point, so it is point focus. So this is a curvature disk, and if we cut it, then we get cephalid disk. Also, this is called cephalid disk. This also does the same thing, but there is a difference between parabolic and dish. Cephalid disk is also a kind of parabolic disk, but with some change. Okay. Now medium and high temperature solar power plant technology. So we have parabolic trough, like I said, a disk curvature which reflects the sunlight focusing on a pipe. Then we have curved mirrors, Fresnel reflector. Then we have solar tower, and we have parabolic disk. Okay, so before I move to this next slide, let me see if there are any questions from you guys. So are you guys facing any issues in lecture slides which you want to discuss or something? So it will be really interesting to know what are the different problems which you guys are actually facing in lecture slides or assignments. So maybe I cannot discuss the, because the assignments which we discuss here are from the previous run of this course, but those assignments are, if you have do it with me in this live session, then that will actually help you guys to get a good understanding about what it constitutes. Okay, so these are very important questions which you need to know. This is very much important when you think of studying or getting a complex understanding of the solar thermal systems or different type of solar systems. Okay, concentrated solar thermal systems. Okay, so if you have any questions, so you can please feel free to ask, otherwise I go to next slides. Okay, so no problem, because when I when, sorry, when I'm teaching, what happens is that I could not see, hear your voices because of the this what you say, the functionality of this Google Meet. So I will suggest you guys to please write down your questions here in the chat box itself, so that I can actually get a good understanding about the different questions which you want to ask or something which you want to discuss. Please write it down in the chat box. Okay, and please feel free to ask. Make sure these discussions are actually like normal discussions on solar thermal systems, so we can also get a good understanding about what you want to say something, or is there anything or any article or something which you read about solar system, solar thermal systems, not solar system. Solar system is different thing. Okay, so systems. Okay, So no problem. Let's move to the next slide then. Now central tower or central receiver system. So basically central tower and central receiver is basically a kind of point focus thing where heliostats are there. Heliostats are basically mirrors, so you can see them here. These are heliostats. Okay, they whatever this sun rays coming to them, they focus it on this tower, and this tower they can reach very high temperature, very high temperature. So easily they can get 800 to 1000 degrees Celsius. So theoretical limit, many books also mention 1500 to 2000 degrees Celsius, but do the theoretical limits. Use field of mirrors to reflect sun. A heliostat uses field of dual axis sun trackers. So there are dual axis sun trackers. So now the question arises, what consists of a dual axis sun tracker? So dual axis sun tracker is that sun moves up and down in the sky, and then it moves east to west. Okay, so with seasonal variation, it has up and down movement in the sky. So zenith angle and altitude angle are changing. Okay, and similarly azimuth angle are also changing. Okay, so and sun moves, so sun has to be tracked throughout the season and throughout the day. So that is why we need a dual axis sun tracker. Sometimes single axis sun tracker are also installed, then you have to uh, track, adjust the screws to make it focus based on the seasons. Okay, so heliostat fields account for 40 to 50% of the total solar power plant cost and can be responsible for up to 40% of the energy losses. That's actually true. Most of the energy is not concentrated here, but can be lost, as we have calculated in the solar chimney also. You can see molten salt retains heat efficiently, so it is used to store heat for a long time. So what happens that these systems can work only during the daytime, solar time. Okay, so I'm not using the word daytime. Daytime can be extended from sunset to sunrise or sunrise to sunset. Okay, but daytime, these only work during a specific duration in which sun has that specific energy available from the sun, so that these can be converted to effective electrical efficiency or heat efficiency. So instead of using water, we use molten salt, which actually captures this heat from here, and then it is stored somewhat underground or here, and then even at night these can be used to generate electricity. Okay, so this is how it works. So these are heliostats. So sun rays are focused on the central tower. This is molten salt. So molten salt can be, the various salt concentrations are there also. So there are various researches going on in energy storage system. Go, you will get to know about all those. So we have various um, type of liquids also, or various energy storage system also, that stores the sunlight. Okay, the solar energy in it. Okay, so cold molten salt solution goes, it gets heated, and then it is stored in the, then there is a thermal exchanger, heat exchanger, a steam generator. So it can, you can imagine it as a boiler in thermal power plant. So these tubes pass through it and steam is generated, steam goes through turbine, electricity is generated from here, and then we have condenser which cools the this steam, and then there is a pump which pumps back it to the steam generator. Okay, so it this is how it works. Then we have parabolic dish system. Parabolic dish collector is similar in appearance to large scale satellite dish. So you have seen the satellite dish antenna. Generally during like a decade ago, or maybe a decade and a half, 15 years ago, these type of disk antenna were there, which focuses the rays, electromagnetic rays from the satellites to that TV signal. Okay, so these are some similar type of things. Okay, but has mirror like reflectors. You can see mirror like reflectors here, and a absorber at the focal point. So this is focal point, we have an absorber here, and these tubes can pass here, and then hot water can come and get stored. Okay. Thermal analysis of solar power plant. So I won't go into this thermal analysis because when I will solve the questions, I will explain this thermal analysis. Okay, I put these slides here so you guys can easily understand what does a thermal analysis means, but I want to explain it when I solve the assignment questions. Okay, so if you have any questions or anything which you want to ask, please feel free to put your questions in the chat box. Let me see if there are any questions. Okay, so there are no questions from you guys. Okay, so no problem. Please feel free to ask any questions till this 8:03. So if you have any questions, please feel free to ask. Let me open the slides also. So these slides are already uploaded. So you guys actually know now where these slides are getting uploaded. Okay, so these are when you go to your Swayam tab or NPTEL tab, then you'll see problem solving tab is there. Click on that, you will go to sheet, and then both TAs we are uploading these slides, so you can access these slides and recording from there. I would suggest please feel free to go through those slides. Okay, otherwise let me share, and if there are any questions which you want to ask, please put your questions in the chat box so that I can answer these questions effectively without any problem. Okay. No questions? Madhav is asking, can we get this recording? So yeah, Madhav, yeah, we can get this recording. So don't know whether I open it or not. So yeah, you can go here, go to courses, go to problem solving session. Okay, problem solving session recordings. Click here to view the problem solving session. So these are the two TAs, Kapil and Rohit. We are the two TAs for this course. Okay, so you can click any of the TAs recording. So this is where you will get all the slides from where we teach. So these slides are uploaded for week 1 and week 2. Okay, so you can refer it from here. Otherwise, you can see the recordings from here also. Okay, so this is from the last session recording. Okay, so if there are any queries regarding this, you can always feel free to ask. And this is the Q&A, that is discussion forum. So if there are any questions, you please feel free to post it here. Like this person has actually uh, posted some questions, like he is not able to download lecture notes, so you can also post it here, and any other questions you want to have a good discussion. Okay, so let's move to the assignment questions, and we will discuss these assignment questions, and then within these assignment questions we will also discuss the what do you say, the different concepts involved in solving those assignment questions. Okay, let's move to these assignment questions then. Okay, so here it is, most of the solar radiation received on Earth's surface lies within the range of. So this is quite what you say, straightforward type of question. So most of the solar radiation lies within the range of 0.2 to 0.4 microns. So microns is basically micrometer. Okay. Which of the following describe the working of central receiver thermal system? So basically, central receiver thermal system, you have sunlight, then focused on heliostats, then focused on central receiver, then we have this turbine, okay, through which molten salts solution pass, and then electricity. So the correct answer is answer B. The operating temperature of central receiver thermal system is, so it's 400 to 800 degrees Celsius. Okay, central receiver thermal power system. Energy balance on the observer of concentrating collector yields. Okay, so QU is basically the useful energy gain. So useful energy gain, whatever energy is basically received from the sun minus whatever energy is actually lost. Okay, so U1 is the lost factor, like heat loss coefficient, and then we have this concentration factor, then this T plate temperature minus ambient temperature. Okay, and then you multiply it with A alpha. So now you get A alpha common, so you will get this equation. Okay, so are you guys understanding about these, how these equations are derived? So this has been explained in the previous lecture also. The condition at which maximum temperature of flat plate collector attains is. So I think this question has been discussed in the previous lecture also. So basically useful heat gain is zero, then only maximum temperature of flat plate collector is actually attained. Okay, so basically useful heat gain is basically whatever heat is received. Okay, then whatever heat is being taken by this this liquid. Okay, this is useful heat again, QU. Okay, so if this is 0, so this system will have all the heat going to raising the temperature. So that's why the correct answer is useful heat gain is 0. Use of so I will not go into this this question until unless we discuss some theory. So let's say I leave you guys here so that you guys can have a good understanding about the theory portion. Okay, let me see if there are any queries available. What is the overlapped glass absorber plate mentioned in week 1 question number 3? So basically, when you say see what you say flat plate collector. So whenever you see a flat plate collector design, so there are two glass plates, glass covers are there. So these are lying one above the other. Okay, so this is what they are referring, overlap glass absorber plate. So they actually help in, the first thing is that they minimizes the heat loss. Second thing is that they help in trapping the solar wavelengths. Okay, so those two are the major functions of this overlapped glass absorber plate. Okay, let's see the questions itself. Okay, so you can see simple flat plate absorbers. So you just have to understand what does these type of things system mean. Done porous absorber plate, and finned absorber. Okay, so please focus on this before I move to the next slide. Okay. So let me explain this. So this is basically a Rankine cycle. Like Rankine cycle is basically used in power plants. Now, what does Rankine cycle mean? So there is a boiler here. Okay. So in place of boiler, we have solar concentrator and all those systems which converts water to or molten salt to steam or something. Okay. And we have this turbine, then we have condenser where heat is rejected, and then there is pump. So if you draw the Rankine cycle on a TS diagram, TS diagram is basically temperature entropy diagram. Okay, so this is the isobaric curve, and then this is isobaric line. Okay, isobaric is same pressure line. So we have this is actually showing the energy input, that is in the boiler in case of this solar thermal. Then we expand it in turbine to produce power. So work extracted is basically H4 minus H3. H is basically enthalpy. But what happens? The problem is that we are not able to, because there are some irreversibilities in the system itself. So we are not able to extract the whole work. So H4 dash, we will are able to extract only H4 dash minus H3 work. Okay. Okay, then we reject heat in the condenser. So H4 minus H1 is actually heat rejected, and heat supplied is H3 minus H2. Now again there is a catch here. It's not H2, it's H2 dash. Why? Because there is some irreversibility in the pump. Okay. So the actual enthalpy is H2 dash instead of ideal enthalpy, which should be H2. Okay, and this is pump input, like the water which is here after the condenser, it is again fed into the boiler or something system. So if you see the turbine efficiency, now the question is that what is this turbine efficiency? Is it first law efficiency or is it the second law efficiency? Okay, so I will give you a hint. It's a second law efficiency. How? You just have to go and search. Okay, otherwise that's how you guys will be able to know what does it mean. So this is basically a second law efficiency. Now the problem is that we have turbine efficiency, we have pump efficiency, we have net work output, that is basically the work output here, H3 minus H4 dash minus H2 minus H2 dash minus H1, that is pump work is subtracted from the turbine work, that is net work output. And we have heat input, that is H3 minus H2. Okay, heat input is basically H2 dash is basically in the form of boiler, that is concentrated here. So pump work is there, then we have cycle efficiency, work done by upon Q. So this is how it is. Okay, so if there is anything which you want to ask here, please feel free to ask. Okay. Okay, so let's move to the assignment question then. Uh, why heat input is H3 minus H2 dash instead of H3 minus H2? Okay, Jay, I will answer this. Okay, so basically, what happens that when you see this TS diagram, okay, so basically, actually, heat input should have been H3 minus H2. This is the ideal heat input. But what happens when their pump starts working? So pump has to raise the enthalpy from H1 to H2, but due to some irreversibility in the pump, because work is being provided here. Okay, so instead of like let's say 1 kilowatt of work has to be done in the pump to reach to make the steam from water from H1 to reach the enthalpy value at H2, but instead of 1 kilowatt it will require 1.2 kilowatt or something because of some pump loss. Any system is not 100% efficient, so there will be some loss in the pump also. So the enthalpy, the actual enthalpy will be reached is H2 dash. So that's why the heat input is basically from H2 dash to H3. Okay, is there anything else you want to know, or did it satisfied your question query? Okay, Jay. So, anything else? Any other question or something? Because only 4 to 5 assignment questions are there. Then we conclude this session. So I'm quite amazing that you guys are asking good questions. Basically, fundamental. You are trying to understand the fundamental of the process. So if you will be able to understand the fundamental, it will be very easy to solve any question. So don't worry, you will be able to solve questions. Okay. So let me go to the side then question slides. I think we had done 5 and then we'll move to 6. So use a booster mirror with flat plate collector. So basically booster, what it does, it increases the beam radiation component of the absorber. So there are two components, beam plus diffuse radiation. Okay, so beam radiation which falls directly to the at perpendicular direction, but diffuse radiation coming from all other directions. So what does booster mirror? So how does booster mirror looks like? This look like this and this work like this. So whatever this sunrise goes here, it also focus it down on the flat plate collector. Okay, so this is the booster mirror, the side mirrors which are installed here. Okay, in the flat plate collector. Now Rankine cycle efficiency of a concentrated thermal power plant is okay. Let me draw the TS diagram itself here. T S. Okay. 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 So this is H3. This is H4. This is H4 dash. This is H1. This is H2. This point. And pump will consume some more energy instead of H2. So H2 dash. Now tell me the Rankine cycle efficiency. I am not going to because I have just like explain this whole thing, TS diagram thing, and how to calculate the Rankine cycle efficiency. So I am sure you guys will be able to answer this. Okay. So for Rankine cycle efficiency, it's very simple. You just have to go work done upon cube, net work done. So net work done is H3 minus H4. So H3 minus H4 is there. and then you have to subtract the pump work from here. Pump work is H2 dash minus H1. Okay, and then whatever is the heat supplied, H3 minus H2 is there. Okay, so the correct answer is answer A. Now the value of heat removal factor of a flat plate collector lies in the range of, so heat removal factor lies in the range of 0 to 1. Okay, in solar vapor compression cycle, efficiency of Rankine cycle increases with decrease in the temperature of heat exchanger, increase in the temperature of heat exchanger, amount of heat supplied to the evaporator, okay, and amount of cold air released from the system. So let's see Rankine cycle here again. Okay, now it says decrease in the temperature of heat exchanger. Let's say this temperature is actually decreased. Amount of heat supplied to the evaporator, amount of cold air released from the system. So yeah, so if this is this heat exchange decrease, so decrease is basically, let's say, decrease in the temperature of heat exchanger, increase in the temperature of heat exchanger. So this temperature is actually increased. Okay, increase in the temperature of heat exchanger. I think this is somewhat confusing because this, if this temperature is actually decreased, then we obtain a much more amount of work. So that will actually push up the efficiency of the Rankine cycle. So maybe it is saying the temperature that is from the outward side. So heat exchanger is like, it is talking about heat exchanger. So heat exchanger are like this. Okay, so this is heat exchanger. This is cold fluid in. Okay, cold in and hot out, and then we have hot in and then cold out here. So the heat from this is given to this. So if we this temperature of heat exchanger decrease, so then heat exchange efficiency of the Rankine cycle will be increased because less energy will be expended here only. Okay, so the correct answer is B. But I feel if we are looking on this perspective, then if we decrease the temperature of heat exchanger in the condenser here, if it is telling about heat exchanger, then we can obtain much more work. Okay, so for me, I think if it is talking about condenser perspective, then option A is the correct option. Decrease in the temperature of heat exchanger. Okay, so let me see if any one has question which wants to understand this concept, or if someone has not got it. No question? Okay. Now question 10. This is the big question. Okay. So we'll solve that question for you. So no problem. I will solve this question for you guys. Alright. So before I solve this question, it's 8:45 and I want you guys to look for a 1 minute or something. So before solving this question, let's see the values which are given. So we have this width of 2 meters. So there is a cylindrical parabolic collector which has a width of 2 meter and then length of 8 meters. So there is a cylindrical parabolic collector. Let's say we are seeing a front view. So it have 2 meter and length of 8 meter. Okay. Then I think instead of drawing like this, we can draw like this. So you guys can have a good idea. So let's say this is a top view. This is 2 meter. This is 8 meter. Okay. Now per unit aperture area is solar radiation is, so let's say S is 400. The observer has a diameter of 55 mm, so observer has a, this is observer tube above it, and it will cast some shadow here. Okay, so this has to be subtracted. So this has an outer diameter of 55 and there is a thickness of 5 mm. So inner dia is 45, 5 mm thickness, 2 into T will be minus. Okay, and transparent envelope is also there, so this is making it a biggie question. Okay, so 85 mm. Okay, so this will consume some heat transfer, has to be taken into account. The collector is designed to heat a fluid enter at entering the observer at 220. Okay, at the flow rate is also given 0.04. Now the value of Cp of the fluid is 3.26. So you know the Cp, Mcp del T. If you want to, the heat transfer coefficient inside the tube is 280. Inside the tube is 280 watt per meter square. Overall heat loss coefficient U is also known. So otherwise we would have to calculate this U. A tube is made of stainless steel. So this is a tube which is made of stainless steel of thermal conductivity 16 with a wall thickness and ambient temperature is TA is 22. Now you need to calculate the heat removal factor. So heat removal factor is basically F. So the formula is already given in the slides itself, but let me what's this. So first thing which you need to do is to calculate the area of receiver and area of aperture. Okay, so area of receiver is pi dl. Okay, so pi into length is 8 meter and pi into 0.55 into 8, so it comes out to be around 1.382. Then we have area of aperture, you need to minus the 2 into 8 minus 0.085, that is the thickness of this diameter of this tube which is casting a shadow. It will cast a 0.85 diameter into 8 the length of the shadow. Okay, so this is AA 15.32. Okay, now we need to know the collection efficiency factor, and the question asks the heat removal factor. So heat removal factor is basically FR, but to calculate FR you need to know the collector efficiency factor. So F dash, which you need to know. So F dash formula is 1 upon UL. Okay, so all of these are taken from slides only. Okay, 1 upon UL plus D naught upon HF. Okay, you know the HF? HF value is this basically. Sorry, not heat transfer coefficient. This is overall heat loss, UI value. This is HF into DI, and because a layer of another layer is also there, so there will be additional terms D naught upon 2K ln D naught upon DI. Okay, here D naught is the outer diameter of the tube, that is 55 mm, and the inner diameter of the tube is 45 mm. Okay, so calculate this. This comes out to be around 0.946. Put the values and get the, okay, and then you need to calculate the heat removal factor FR. Use the formula. Simple. Use the formula m dot Cp. You know, AR you know, UL you know, 1 minus exponential. Okay, minus AR UL F dash which you calculated here. Put it here. Okay, upon m dot Cp. Okay, so this comes out to be around 0.89. So this is what is asked in the question, heat removal factor. Okay, so the correct answer is 0.89. Answer C. Now useful heat gain. So this is also important. Useful heat gain is basically QU equal to aperture 15.32 and FR which you calculated, then S minus AR into UL upon AA TPM plate temperature minus the ambient temperature 22. So put the values, you will get it to be something around 2787. Okay. So the correct answer is answer A. Now exit fluid temperature. Okay. So this is very simple. You know this value, exit fluid temperature. So you know this useful heat gain value. So thus just MCP del T. Okay. So you know the entrance 220 is the entrance. Okay. And 2787 is the zero point 0.5 is the heat gain. So put the values here. M you know M is 0.04 or something. 0.04 Cp value you know fluid. Then entrance temperature you know 220 or something. Then put the values, you will get the values as 241.4 is the fluid temperature. Okay. So this is what all the questions have been solved. So let me see if there are any questions from the students. Okay, so no questions are there from the students. So please look into it. I am just, and if there are anything which you want to ask, please feel free to ask. Okay. Any question, guys, which you want to ask regarding this? So these are not big questions. You just have to understand what the question is asking. So if there are no questions, then I conclude this session here. So thank you guys. Thank you for this various question which you asked, and we had the interaction for that. So thank you once again. We'll meet again on the Tuesday, 7 to 9 p.m. Okay. Thank you. Thank you once again.